Our multidisciplinary design team, consisting of Michael Hall, Matt Hummel, Colton McKay, and Nathan Lee, is working with the Rose-Hulman Rover Robotics team to redesign, build, and program a robotic arm for use in the University Rover Challenge. This challenge is designed to simulate the tasks required for a Mars rover by traversing difficult terrain, finding GPS waypoints, and operating equipment while remotely operated from distances of over a kilometer away. The University Rover Challenge has several requirements for tasks that require robotic manipulators, including lifting weights, pulling ropes, opening drawers, typing on keyboards, pushing buttons, flipping switches, operating joysticks, plugging in USB sticks, and more. We have distilled these tasks into a design requirements list in order to focus on the specific capabilities our arm must have in order to complete all of the tasks in the competition. Previous years' iterations of the arm have been able to succeed with some of these tasks, but have failed to consistently complete all the tasks within the competition time limits. Key failure points of previous arms have been their lack of rigidity and difficult operator controllability during competition. At the conclusion of last year's competition, the arm was badly damaged, and we have decided to use this opportunity to undergo a complete redesign from top to bottom, hardware and software.
Our new arm design has a long list of upgrades over the previous generations. Starting with the overall design, we are moving to a full 6-degree freedom robotic arm instead of the previous 5-degree of freedom designs. This allows us to have additional dexterity and maneuverability to complete tasks which require fine motor skills. Each joint of our arm has been mechanically redesigned to increase rigidity and minimize backlash. Both of these factors tremendously increase the controllability of the arm, as flexibility and backlash in the arm joints cause oscillation and unpredictable behavior at the end effector. Many of our joints have also now moved to a belt-driven design, allowing us to move the motor mass closer to the base of the arm and further reduce oscillations at the end effector. Joints 4 and 5 utilize a shaft-and-shaft design to push the joint 5 motor even further away from the end effector. The end effector has also been reimagined to a design with increased grip strength and finger dexterity. Previous gripper iterations have struggled with small or oddly shaped objects, and our new gripper features squishable, high-friction fingertips to increase the range of objects which can be manipulated. The software and control system of our arm has also been rebuilt. The control system, as with the previous arms and the Rover system, operates on the Robot Operating System, known as ROS. ROS is frequently used with both research and commercial robots.
The motor controller and position and velocity measurements for each joint are controlled by an on-arm microcontroller, which communicates with the ROS server on the rover. The velocity data is numerically derived from the joint encoder positions in real time and filtered to allow for velocity PID control on each joint. In order to better control the rover arm, we have implemented inverse kinematic control, which allows the operator to command the position of the end effector in Euclidean space while the arm joint moves in tandem to meet the operator's commands. This year, we have written our own velocity-based inverse kinematic solver. The new solver is able to take directional commands from the operator and convert them into velocities for each individual arm joint. Finally, since our arm must be remotely operated from great distances, it is important that the operator has a camera view of the arm. In previous competitions, we have struggled with depth perception and visibility. To fix this, we have added multiple camera views from different angles and perspectives to allow for easier operation.
Building a robotic arm is a complex project involving many different engineering disciplines. Unlike previous arms built by the Rover Robotics team, this arm has been designed to withstand multiple years of competition. Therefore, the documentation and knowledge transfer to future team members is a critical part of our mission to providing a working arm for future competitions. The documentation for the arm consists of a team Git repository for all software and PCB designs, while the mechanical designs are stored on the team GrabCAD. We have also created a full documentation wiki to provide instructions on operating, maintaining, and updating the arm as future competitions may require. With these resources, the team may continue to have supported equipment that they may rely on and build upon in the future. Robotics is inherently multidisciplinary, and we made sure to leverage our team's varied experience and skills. Our end product is functional, sturdy, and should serve as a very useful tool for the Rover team to use in many years to come.